definitions that we have so far for kinematics. Remember, kinematics is the definition is the description of motion. So the variables that describe motion include time, which I don't have down here, distance, path length, position, which we called x, but it could be called other things. Right now we're calling x in one-dimensional motion. Displacement, delta x equals x finals minus x initial. Average speed, which is distance over time elapsed. Average velocity, which is displacement over time elapsed, or delta t. Instantaneous velocity, which is taking the average over a very small time, or the derivative, or the slope of the position versus time. I added the slope comment. Average acceleration, which is the change in velocity of a change in time. And instantaneous acceleration, which is, again, the limit as del t goes to 0, taking the change in velocity of change in time over a very small time interval, which is the slope of the v versus t graph, or derivative of the velocity graph. So those are the definitions for kinematics in one dimension. There's a lot of information here, but the basic things, the things that we use frequently, are understanding what delta x means, change in position or displacement. Understanding v average is delta x over delta t. Whoops, I skipped one. Understanding average speed, the difference between average speed, total distance traveled over delta t. Understanding that instantaneous velocity is now dx dt, average acceleration versus instantaneous acceleration. And make sure that you understand, even if you don't know derivatives, if you haven't done much calculus and you're not comfortable with derivatives, that we'll get there in a short time, but that is the slope of the x versus t graph, dx dt, or the slope of the v versus t graph. It's a slope of a graph at any point, right? So if we talk about the slope at a point, the derivative means the slope at that point. So if you understand all that, I've just sort of summed it up into the purple boxes from the other page, that these are the things that we need to know the definitions of. In addition, you need to know the difference between displacement and distance, and average speed and average velocity. So I guess I sort of left those off, distance over time. Now, a couple things we need to review here. The first is to remember at the end of class, the very last thing we said was about when is, for example, average velocity equal to instantaneous velocity, or when is average acceleration equal to instantaneous acceleration, a average equal to a instantaneous, or v average equal to v instantaneous. Those are two separate questions. They're equal when you are traveling at a constant value. So a average is equal to instantaneous acceleration when you're traveling at a constant acceleration. V average equals v instantaneous when you're traveling at a constant velocity. Now in class we said we will typically, unless you're otherwise told, we will deal with constant acceleration problems. So unless you're otherwise told, and we will have situations where you're told we don't have a constant acceleration, but otherwise we'll typically deal with constant acceleration problems, and in that case the average acceleration is equal to the instantaneous acceleration. What that means is, if I'm traveling constant acceleration, imagine what that looks like on a graph. On a graph of what? Of velocity versus time, right? On a graph of velocity versus time. If I'm traveling at a constant acceleration, then that means that if we look at the last equation here, right, the equation for instantaneous acceleration. If I'm traveling at constant acceleration, remember dx dt, if you know nothing else, you should know that means the slope. Oh, shoot. I made a mistake. Acceleration is not dx dt, of course, it is dv dt. Hopefully you caught that mistake long before I did. So dv dt, means the slope of the velocity versus time graph. If the acceleration is constant, what does that say about the slope? If the acceleration is constant, then dv dt is constant, then that literally means the slope of the velocity versus time graph is constant. So a graph with constant slope would look like that. Whoops, like a straight line, right? A line with constant slope. So it's got a constant slope. And so then if I ask, okay, well that shows me that shows velocity versus time. The instantaneous acceleration, remember, is the slope at any point. And again, we said we're traveling at constant acceleration. So this is a constant acceleration graph. A constant acceleration graph has a constant slope on the velocity versus time graph. That means that at any point, right, if I look at any point, any of these green points that I'm drawing in here, that the slope at any of those points must be the same. That means this is a straight line, a line with constant slope. But that also means that the average velocity between any two of these green points, the average velocity is the slope between those 2 points, is the same as the slope of the line at any point. So just by looking at the graph, you can see that the average acceleration between any 2 points that you should put on the graph equals the instantaneous acceleration, the slope at any point on the graph. So for constant acceleration, that is true. Okay, what about for constant velocity? If I'm traveling at constant velocity, then that's going to be true for the velocity average. Again, you can look at a graph. We can look at velocity on a graph, which is position versus time. And if I'm traveling at constant velocity, let's just make a different kind of line. If I'm traveling at constant velocity, it means it's something with a constant slope. And so constant velocity is a graph of x versus t with constant slope. And that just says that by the same argument that if I look between any 2 points, the average velocity, the slope between 2 points, is equal to the instantaneous velocity, the slope at any individual point. But here's where you need to be super careful, right? In general, I'm going to repeat myself, in general in class, it's okay to assume constant acceleration unless you're otherwise told, but it's not okay to assume constant velocity. So in general, you should not assume that the average velocity is equal to the instantaneous velocity, because we're not assuming constant velocity. If you know that the velocity is constant, then indeed it is correct, but we are generally going to be dealing with constant acceleration problems where the velocity is changing. So the average velocity is not equal to the instantaneous velocity. And here's the mistake that at least 50% of you will make at some point. Notice now I'm going to put a box around the average velocity equation. Velocity equals displacement over time. You will use, instead of that, you will say v equals delta x over delta t, and you will use that equation, which is incorrect, right? Because v is instantaneous velocity. It's incorrect unless we're traveling at constant velocity. So this is only correct if we're traveling at constant velocity. And at least 50% of you at some point, hopefully you won't because you'll pay attention to this very important point, but from experience, 50% of you will use the constant velocity equation for a problem that does not have constant velocity, where the velocity is changing. So this is correct only if the velocity is constant. Okay, so let's do a simple kinematics example. Let's say, I've already drawn the picture. Let's say I have a car that is accelerating from rest, v0 equals 0. Initial velocity, v0, initial velocity equals 0. And it's accelerating at a constant velocity of positive 3 meters per second squared. I'll talk about subscripts and signs in a moment. Let's say that we're doing a one-dimensional problem. It's moving in the x direction, and the car accelerates for 3 seconds and goes a total of 24 meters. So the question I'm going to ask is, what is the final velocity? What is the velocity after 3 seconds, or after it's accelerated 24 meters? So we look at this and we say, oh, okay, so v equals delta x over delta t. I want to know the velocity after 3 seconds. It's 24 meters over 3 seconds, which is 8 meters per second. And wrong. Incorrect. Wrong answer. Why? What did I do wrong? How come that's wrong, right? We know velocity is distance over time, or displacement over time, sorry. Why is that wrong? Well, it's because this, again, I just said, right, assumes a constant velocity. This equation in the red box is true only for a constant velocity. And is there a constant velocity here? No, it is accelerating. It's changing its velocity the whole time. So this is not valid. It would only be valid if it was going at constant velocity. So we need to look at the correct kinematic relationship, look at all the kinematic relationships and the ones that hold, and we have acceleration equals delta v over delta t. So therefore, delta v equals a delta t, and so therefore, delta v equals 3 meters per second squared times delta t, which is 3 seconds, and so delta v is 9 meters per second. And so what we end up getting is delta v is 9 meters per second, but what's v initial? Right, delta v, I gotta do this on the side. Delta v equals v final minus v initial. I wrote v initial as v0. And so 9 meters per second equals v final minus v initial, which is 0. So therefore, v final equals 9 meters per second. Okay, so the final velocity is 9 meters per second, not 8 meters per second. Check. Okay, a couple of really important points I'm going to make here. First of all, is just making sure you understand your kinematic definitions and you use the correct ones for a given problem. In this case, we're not traveling constant velocity, so we can't use the definition of average velocity in order to find the final velocity. But the second thing to note is a couple things that I do, and I don't do them just for your sake. I do them because it's the only way I know how to successfully solve problems. One is to make sure that we carry our units all the way through your problem. Make sure you're carrying your units, right? See here where I used meters per second, or here I used meters per second squared in seconds, and make sure that the units cancel out and you get the right thing, right? Meters per second squared times seconds indeed is meters per second. You're just going to have to get used to manipulating letters the same way you manipulate numbers. Another thing I did is I drew a picture. And on that picture I indicated all the quantities I could possibly draw. I cannot solve a kinematics problem without drawing a picture. It's too hard to keep it all in my head, and you ought to be drawing pictures too. So this is just a couple of hints. Is again carefully choosing the relationships that suit the problem. You don't have to memorize them, but you should have a list of the relationships handy. Making sure to carry your units through and making sure to draw pictures. Let me talk real quick about subscripts. You should always have subscripts on your variables if it helps us identify what they are. For example, let's just go back to what I did in the previous page. Delta v equals v final minus v initial, right? That's the definition of delta v. But if we're talking about a problem where we're asking what is the time, or we're giving the time between initial and final, as I said in class, typically, unless you're told otherwise, unless the problem specifies, you can start at the initial point. You can just assume that initially t initial is equal to 0. And then our final point, final, v final, we're just going to call, try again. Initial time ti equals 0, final time tf, we often just call t. Right? So we're going from 0 to t. That's the same as going from t initial to t final. It's just notation. And so because we go from ti equals 0, we often call that initial velocity, the v initial, we call it v0 because it's v at t equals 0. You can call it v initial, vi if you want, or v0. This is just notation to indicate which velocity we're talking about. And you need to use whatever notation makes the most sense to you. You can always carry your VIs and VFs, but often we'll just call VI, the initial velocity, V0, and VF, the final velocity, just V, because we've already defined the initial and the other one's going to be the final. So this is just a notation thing. V0 does mean V initial, they're the same thing. And the same thing goes for position. We can talk about X initial and X final, or X0 and XX as being the final position.